So till now we were talking about only steady state heat conduction. Now let us see some outlines of unsteady heat conduction. When I say unsteady heat conduction, temperature will be a function of time. Time becomes important. So temperature may increase or decrease with respect to time depending upon the type of system we talk about. As a result, heat transfer rate Q will also vary with respect to time. You may note that here this Roman letter tau is used to represent the time. Then this unsteadiness prevails in the beginning and near the end of any operation. First 10%, last 5% unsteadiness. In the middle of 85% we are going to have steady state heat transfer. Okay? So always unsteadiness prevails near the beginning or near the end of any operation. For instance, if you imagine that we have a large furnace, very big furnace, maintained say at 300 degrees centigrade. Let's imagine. We have big furnace maintained at 300 degrees centigrade. Let us suppose we have a metallic piece. A metallic piece initially at 20 degrees centigrade. Let us imagine that this metallic piece is inserted into the furnace. And we embed a thermocouple and we make a note of how the temperature of the metallic piece is varying with respect to time. And if we show this graph, x-axis we take time, y-axis we take temperature. Initially, the metallic piece is at 20 degrees centigrade. Furnace is maintained at 300 degrees centigrade all along. Then if you note the temperature, this temperature is going to rise very quickly in the beginning, very quickly. Then after some period of time, the temperature difference between the metallic piece and furnace remains more or less same. They assume steady state condition, which means that this entire heat transfer process can be split into two distinct zones, zone 1 and zone 2. Here zone 1 is known as steady period and zone 2 represents unsteady period. Zone 1 represents steady period and zone 2 represents unsteady period. You can see that here the temperature is changing very quickly with respect to time. As a result, the heat transfer rate from the furnace to the metallic piece will be a function of time in this particular zone. Whereas in the second zone, the heat transfer rate remains the same, independent of time. Then comes the question, how long we have to wait? It may depend upon the type of system. That's why in the beginning we said that for a system to be steady, it must be in the given environment for longer periods of time. For a system to be steady, it must be in the given environment for longer periods of time. Please note that zone 1 is unsteady period, zone 2 is steady period. Just interchange. In zone 1, temperature is varying very quickly with respect to time, that is unsteady period. Zone 2 is steady period. Which means that for a system to be steady, it must be in the given environment for longer periods of time. Till now, we have waited for this much amount of time. Now we like to go to the left. We like to encroach into the unsteady period. We will see what exactly is going to happen. Okay? This is a typical heating problem in a furnace. Right? One can as well consider a cooling problem. Just mirror image of that. Let us imagine that we have a refrigerator at 2 degrees centigrade. Let us imagine we have a refrigerator at 2 degrees centigrade. And we have some fruit, some item at initial temperature of 20 degrees centigrade. We take this fruit and keep it inside the refrigerator. Please note that this is a refrigerator. A cold space. This is a furnace, a hot place. Then we make a measurement of the temperature of the fruit. Then we plot the result. X-axis we take time. Y-axis we take temperature. Initially, the fruit is at 20 degrees centigrade. All along, the refrigerator is at 2 degrees centigrade. And if you notice the temperature variation, it's going to drop very, very quickly in the beginning. Which means that there will be unsteady period in the beginning, 1. During which temperature is changing very sharply with respect to time, followed by steady period. Okay. This is the unsteady period, wherein heat transfer rate is changing very sharply with respect to time. And is a steady period in which heat transfer rate remains the same, independent of time. So in the beginning we have unsteadiness, at the end we have unsteadiness, in the middle it will be steady. Okay. So let us see how exactly this time has to be taken into account. So the moment I say unsteady conduction, time comes into picture. In addition to time, we may have only X, 1D unsteady, X and Y, 2D unsteady. Like that we can include other parameters also depending upon the requirements. But time will be common. Time will be common. When it's a steady, only X, 1D unsteady, X and Y, 2D steady. Like that we can classify steady state systems. When it's a steady state systems, time has no business. When it's an unsteady state system, time becomes very, very crucial. Okay. Right. This is about the general introduction, about a cooling system, about a heating system. Let's try to talk about different types of unsteady systems. Types of unsteady systems. Types of unsteady conduction system. That's what exactly I mean. Broadly, we can have two types of unsteady systems. Broadly, one is periodic unsteady systems. Next is non-periodic unsteady systems. We can have two categories of unsteady systems, periodic and non-periodic. The name itself indicates, in a periodic unsteady system, temperature will be a periodic function of time. Temperature will be a cyclic function of time. Physically speaking, we get the same temperature again and again after a definite period of time. That is the meaning of periodic unsteady systems. If we show this schematically, x-axis we have time, tau. Y-axis we take temperature. X-axis we have time and y-axis we take temperature. We will have two temperatures. One is maximum temperature, upper limit. The other is minimum temperature, lower limit. Then of course, between these two limits, one can always have the average temperature, T average. Then the temperature varies periodically between these two limits, something like this. Temperature is varying periodically between these two limits. That's why we call it as a periodic unsteady system. A particular temperature, let us say you want to get this temperature, we are going to get again and again. You are going to get it here, you are going to get it at this instant, you are going to get it at this instant, and so on. After few seconds or after few minutes, you get the same temperature repeatedly. Since there is something certain between temperature and time, periodic unsteady systems are also called as quasi-steady systems. Quasi means almost, very close to. Quasi means very close to. So there is something certain, something definite about the temperature and time. We can come across variety of systems having this particular behavior, like IC engines, cooling of IC engines. That can be modeled using these periodic unsteady systems. The IC engines undergo cyclic process. Then power plants, refrigerators, they all undergo periodic unsteady systems. They all undergo periodic unsteady heat transfer. Okay. Non-periodic, which means that temperature may decrease or increase continuously. A particular temperature we get only once for all. Like if we take a non-periodic system, x-axis time as usual, y-axis temperature, then temperature may decrease continuously, something like this. This we call it as cooling. Or temperature may increase continuously. This we call it as heating. Okay. So temperature may continuously decrease or continuously increase. We are not going to get a particular temperature many number of times. I want to get this temperature during cooling process as only at this instant. Maybe at 30th second, maybe at 45th second, never again. Okay. Again, you got so many practical systems having this behavior. Like examples for non-periodic systems, cooling of billets. Then water heaters. Domestic water heaters, temperature continuously increases with respect to time. No question of getting same temperature again and again. Then heat exchangers. These are some of the systems in which we experience non-periodic unsteadiness. So here temperature is varying periodically, here temperature is varying non-periodically. First case, there is something very sure between temperature and time, we call it as quasi-steady. And second state, nothing sure between time and temperature. Now let us focus more light on non-periodic systems because of two reasons. First reason is that they are easy to understand, easy to interpret. And second reason is that many of the practical cases belong to non-periodic. Leave about special case of IC engines, power plants and so on. They are also important. Periodic we cannot avoid, but they become very complex. We have to have some trigonometric functions, making it a bit complicated. As far as our syllabus is concerned, non-periodic is enough. So now let us focus more on non-periodic unsteady systems. When it's non-periodic, 100% unsteady. There is nothing certain between temperature and time. When it's a periodic, there is something certain. That's why periodic systems are also called as quasi-steady systems. Right. Now let us elaborate non-periodic unsteady systems. Let us focus more on non-periodic unsteady systems. Let us imagine we have a general non-periodic unsteady system, something like this. Okay. Again, please note that non-periodic unsteady system is a very big area, very vast. We want to have a pinpointed discussion, so that we can use available mass, so that we can simplify the analysis, so that we can get some end results. That's the idea. We cannot talk just about unsteady conduction like that. Unsteady conduction is a very broad area. Periodic, non-periodic. Periodic we are avoiding deliberately. Non-periodic. Again, non-periodic unsteady systems are very vast, very big. So we like to further pin it down. For this purpose, we are considering a general non-periodic unsteady system. And let us pick up 3 points. Point P inside the system. Point Q on the surface, point R in the fluid. Let's take 3 typical points, P, Q, R. P is inside point, Q is surface point, R is outside in the fluid. Let us imagine that P is hottest, followed by Q, followed by R. We are providing a direction for heat transfer. You can even have otherwise. R greater than Q, greater than P, but we are beginning with this proposition. Inside point is hottest, then surface point, then the fluid temperature. As a result of this temperature difference, there is going to be heat transfer from P to Q by conduction, Q tau. I am writing in brackets tau, indicating that it is unsteady. And the magnitude of this Q tau depends upon a parameter known as internal thermal resistance. Represented by R internal, mathematically given by L upon Ka, degree centigrade per watt. How much heat transfer is going to take place internally, that is by conduction, from P to Q is influenced by internal thermal resistance given by L by Ka. Here L is the distance between P and Q. A is the area available for heat transfer. K is thermal conductivity of the material under consideration. K is thermal conductivity of the material. Then there is going to be heat transfer from Q to R by convection, that is going to be Q1 tau. I am using 1 deliberately because it is unsteady. And the magnitude of this Q1 tau depends upon a parameter known as surface thermal resistance. Or SUR, which is given by 1 by HA, degree centigrade per watt, where H is the convective heat transfer coefficient of the medium, A is the surface area available. So what we are proposing, we are taking a system, a non-periodic unsteady system, and we are picking up 3 specific points. P inside the solid, Q on the surface or outside the solid. And we deliberately say that Tp is greater than Tq is greater than Tr, such that we can have heat transfer taking place from P to Q by conduction and from Q to R by convection. Q tau is conduction, Q1 tau is convection. Then the magnitude of Q tau is influenced by a parameter known as internal thermal resistance, L by Ka. We can as well call it as conductive resistance. Deliberately I am using the word internal because it's going to have some sense later on. Then there is going to be heat transfer from Q to R by convection. That is influenced by surface thermal resistance. We can as well call it as convective resistance. And here L is the thickness or the distance between P and Q. A is the area available for conduction and this A is the area available for convection. Usually both of them are same. Then depending upon relative magnitudes of internal and surface thermal resistances, non-periodic unsteady systems can be categorized into three. Depending upon relative magnitude, the word relative must be highlighted here. Depending upon relative magnitudes of internal and surface thermal resistances, these non-periodic unsteady systems can be categorized into three types. First type, systems with negligible internal thermal resistance. Second type, systems with negligible surface resistance. Third type, systems with both the resistances on par with each other. Okay. So we are trying to have further categorization of non-periodic unsteady systems. Whenever you want to have any classification, you must have some basis upon which we can classify. That basis we are creating by way of this particular example, by way of this particular figure. We are considering two resistances, one is inside the system, the other is the surface, on the surface of the system. Please note that here we are looking at different types of non-periodic unsteady systems based on relative magnitudes of R internal and R surface. Here the word relative is very important. Relative, we never ever look at absolute. Relative magnitudes. As an example, if I look at a number like 8, some number is given to me, 8 number. If I look at it absolutely, we cannot comment anything about that 8. Absolutely no comparison. 8 may be anything. But when I make a relative comparison of this 8 with a number like 10 power 12, 8 becomes insignificant. This number 8 has got its own magnitude, no doubt about it. But that gets nullified, that gets insignificant when you are comparing with 10 power 12. That is the meaning of relative magnitudes, which means that we look at both these numbers simultaneously. Then we begin to realize that this 8 can be ignored. Same 8 becomes too magnanimous, too big when it is compared with 10 power minus 12. Same 8 becomes too much when it is compared with 10 power minus 12. Now what we do, we look at 10 power minus 12 and 8 and this 8 becomes too big, too magnanimous because we are comparing it with this. Earlier when we look at the upper side, 8 is insignificant. Same 8 becomes too much when you are looking at downside. That is the meaning of relative magnitudes. Okay. So here we are trying to have same sort of discussion, and depending upon relative magnitudes of R internal and R surface, one can have three types of non-periodic unsteady systems. And if you look at them one by one, first, systems with R internal extremely small compared to R surface. Systems with negligible internal resistance. Next, let me give some space. Systems with negligible surface resistance. Systems with R surface extremely small compared to R internal. Next, systems with R internal on par with R surface. Systems with R internal on par with R surface. Okay. What is the meaning of it? First, we have systems with negligible internal resistance. Then we have systems with negligible surface resistance. Then you have systems with R internal and R surface almost equal to each other. Right. To make it better, let us look at the expressions for R internal and R surface. R internal is given by L by Ka. L is the distance that is finite. A is the area that is also finite. For the given length, given thickness, given area, R internal is inversely proportional to K. At the same time, for the given area, R surface is inversely proportional to H. In order to have very small internal resistance, K must be as much as possible. Theoretically, K should go up to infinity, theoretically. At the same time, H must be finite to see that R surface is big. That is, systems with very large value of K and finite value of H. When I say large value of K, R internal becomes extremely small. We don't leave it there. We also look at H, relativity. Finite value of H makes R surface big. So R internal is very, very small compared to R surface when K is too much and H is finite. Similarly, when you want to satisfy second requirement, this must be very small. For that purpose, H must be very large. Theoretically, it should go up to infinity. At the same time, this must be big. That can happen when K is finite. Which means that for a system to have negligible surface resistance, H must be as much as possible, theoretically infinity. At the same time, K must be finite. Right? Exactly opposite. Large value of H will make R surface negligible. Finite value of K will make R internal magnanimous, big. Earlier, large value of K will make R internal very, very small. Finite value of H will make R surface big. We can never ever talk about only K or only H independently. It's not absolute comparison, relative comparison. That's why we said, depending upon relative magnitudes of R internal and R surface. Okay, we look at both the resistances in tandem, simultaneously. Then, in order to have both the resistances comparable, K and H, both of them must be finite. K finite will make R internal big, H finite will make R surface big. Now we can reclassify non-periodic unsteady systems as systems with large value of K and finite value of H. Next, systems with large value of H and finite value of K. Next, systems with finite values of K and H. Then somebody may ask, what happens if both K and H are very large? When both K and H are very large, we don't get anything useful. That we'll see later on. Okay? Let's try to have electrical analogy of this discussion. That's going to give a clear idea of what we are doing. Electrical analogy. Okay? We have 3 points, we go in the reverse direction. First 3. We have point P, right? Point Q, between P and Q, we have R internal. Point R, between Q and R, we have R surface. Conduction taking place at a rate of q tau. Convection taking place at a rate of q1 tau. Perfectly correct. This is electrical analog. This is electrical analog of a system with both the resistances comparable. P is different, Q is different, between them R internal. Q is different, R is different, between them R surface. Because both the resistances are comparable. If you go to the previous case, what is happening? P is there anyway, R internal is there, Q is there, but R surface is 0. As a result, Q and R will coincide. R surface is 0. Why R surface is 0? It's very, very small. Why it is very small? H is very large. Temperature is changing from P to Q inside the solid, right? Temperature is changing from P to Q inside the solid because of finite value of K. But Q is same as R, surface temperature is same as fluid temperature because H is extraordinary, surface resistance is 0. If we look at the first case, the electrical analogy of first case, here what happens? Internal resistance is 0, therefore P and Q will coincide and we have only surface resistance working. Since internal resistance is 0, temperature is not changing inside. P and Q are coinciding, you can see here. Because this is 0. Why that is 0? K is very large. But surface resistance is there. As a result, Q and R are different. Why surface resistance is there? H is finite. Now, if at all you have a system like K is equal to infinity and H is equal to infinity. If at all you imagine a non-periodic unsteady system with infinite values of K and H. When I say infinite value of K, internal resistance is 0, P and Q will coincide. When I say infinite value of H, surface resistance becomes 0, Q and R will coincide. It becomes a dot. When it's a dot, no potential, no heat transfer, it's of no use. Temperature is not changing between P and Q because of very large value of K. So P and Q are coinciding. Like what you have here. Temperature is not changing between Q and R because negligible surface resistance or infinite value of H. Q and R are coinciding, like what you have here. Here infinite value of K, P and Q are coinciding, infinite value of H, Q and R are coinciding, but when you put them together, all 3 points will coincide, no temperature variation anywhere, no heat transfer. That situation does not arise. In order to have heat transfer, one of the K and H must be finite. H is finite, temperature is varying on the surface from Q to R. K is finite, temperature is varying inside from P to Q. Both are finite, temperature is varying inside from P to Q, on the surface from Q to R. Right? This is electrical way of looking at different types of non-periodic unsteady systems. Right? Now let us look at the same systems physically by way of graphs. We get something very interesting. Okay? First is, we are trying to do different ways of classification. First is based on relative magnitudes of R internal, R surface. Second is based on relative magnitudes of K and H. Third is electrical. Fourth is physical. And when you combine them, you get a very good idea of these non-periodic unsteady systems. Okay? Let me have this space. So we have systems with negligible internal resistance, large value of K, finite value of H. First one. Systems with negligible surface resistance, large value of H, finite value of K. Second one. Systems with both the resistances comparable, which mean that finite values of K and H. Now let us consider same situation in a different way. Let us consider an ordinary plane wall. I am talking about first system, ordinary plane wall. We have a plane wall, something like this, of some thickness. This is some thickness L. And both sides you have got a fluid at a temperature of T infinity. Initially, the entire system is at Ti. Initially, at tau is equal to 0. When you go to the surfaces, temperature is dropping from the surface value to the fluid value. From Ti to T infinity. You can see that Ti is same everywhere. Everywhere Ti only, inside. Because of large value of K. But the moment you go to the surface, temperature is dropping because of finite value of H. P and Q are same, but Q and R are different. If you take some instant of time tau 1, entire system is assuming some temperature T1, tau is equal to tau 1. But the moment you go to the surface, it is going down to the fluid temperature. Initially, entire system is at 300 degrees centigrade. After 60 seconds, after 1 minute, entire system is assuming 250 degrees centigrade. You can see temperature is same everywhere. Rapidly, the entire system is going down to T1. After some other period of time, temperature within is equal to T2. Same thing, it won't change with location. But when you go to the surface, it will fall down to the fluid temperature. And so on. Temperature is varying on the surfaces because of finite value of H. It's not varying inside because of infinite value of K. No internal resistance. Entire system is isothermal system. Perfect conductor, you can see. K is infinity. Okay. And mathematically in these systems, you can note that temperature is a function of time only. Location has no business. Initially temperature is 300, after 1 minute temperature is 250, after 2 minutes temperature is 220 and so on. Where? Everywhere. We don't bother about the location. We bother only about the time. Okay. If you look at the second category of systems, slightly complicated, second category of systems, again we take a similar plane wall having finite value of K, infinite value of H. Initially temperature is varying as a function of x, some function of x, tau is equal to 0. But the moment you go to the surface, surface temperature is same as the fluid temperature. Temperature is varying inside because of finite value of K. It's not varying on the surface because of infinite value of H. If you take some other instant, temperature is becoming some T1x inside. But the moment you go to the surface, it is immediately coming down to the fluid temperature. Q is same as R. Ts is same as T infinity. But inside P and Q are different. It's changing. If you look at some other instant, temperature may assume some other function T2x inside. But when you go to the surface, it's same as outside temperature and so on. Temperature is varying inside because of finite value of K. It's not varying on the surface because of infinite value of H. If you look at mathematically, in these systems, temperature is a function of location and time. At any time it is varying from location to location. At any location it is varying from time to time. It's as good as 2D problem, two-dimensional problem. But good thing about